Welcome to a new series, By a Few Degrees, where direction, not chance, writes history. Only on your dose of Wowness.
In July 1994, astronomers all over the world pointed their telescopes at Jupiter and watched something that had never been observed before in the history of astronomy. A comet, already torn into more than 20 pieces, slamming into a planet one fragment at a time, over 6 days, live. Some of those impacts released more energy than every nuclear weapon on Earth combined. And the reason we got to watch it happen at all tells us something unsettling about what could have happened here instead. This is day 9 of By a Few Degrees. We're back in deep space for the final 2 episodes of this arc. Subscribe now so you catch tomorrow's finale. It closes out everything we've built toward. Before 1994, planetary impacts were historical reconstructions pulled from ancient craters and fossil records. This was something different, humanity's first live broadcast planetary defense wake-up call. In March 1993, astronomers Carolyn and Eugene Shoemaker, along with David Levy, spotted a bizarre anomaly while conducting a routine survey for near-Earth objects. Instead of a single, compact, icy nucleus, they discovered a string of pearls, a chain of more than 20 distinct comet fragments trailing across the sky. To understand how a comet breaks, you have to look at the physics of tidal disruption during a close pass in 1992. As it approached Jupiter, the planet's massive gravity pulled harder on the near side than the far side. This differential stretching force overcame internal cohesion, tearing the nucleus into a linear chain of debris continuing along its orbital path. The Shoemaker-Levy team had discovered the shattered remnants of a gravitational execution, a chain of debris locked onto a direct collision course with the planet that broke it. This timeline chart maps the arrival of fragments between July 16th and 22nd, 1994. Pieces struck Jupiter sequentially over 6 days. This multi-day bombardment stands in stark contrast to the single massive energy spike in models of the Chicxulub impact. To document the event, astronomers pointed every major telescope on Earth, along with the Hubble Space Telescope and the Galileo spacecraft, toward the impact sites. If you want to see how this connects directly to tomorrow's finale about humanity actually doing something about asteroid threats, make sure notifications are on. It's the payoff for this entire arc. Watching those fragments strike the atmosphere in sequence moved planetary impacts out of the realm of theoretical modeling and into raw, undeniable reality. The aftermath was visible even through small telescopes, massive, dark, swirling impact scars that lingered in Jupiter's high-altitude cloud bands for months. Analysis of the energy release showed that individual fragments yielded the equivalent of hundreds of thousands of megatons of TNT, several of them releasing more energy than the world's entire nuclear arsenal. This diagram overlays the diameter of Earth directly onto one of those impact scars. The atmospheric bruise left by a single fragment was larger than our entire planet. Observing how those scars chemically reacted and dispersed in the high-altitude winds gave scientists their first empirical baseline for what happens when a large body strikes a planetary atmosphere. Jupiter provided a cosmic laboratory, yielding the foundational observed data that underpins all modern planetary defense risk assessments. Tidal disruption is a universal law of physics, not a phenomenon unique to Jupiter's gravity. A fragile comet passing close enough to Earth could undergo this exact fragmentation, turning a single threat into a sequential chain of impactors. While Jupiter's deep gases could absorb the energy of these fragments, Earth's thin atmosphere and solid, rocky crust would face a sequential, multi-day bombardment that our planet could not replicate or absorb. Modern astronomers actively track known near-Earth objects of this scale, and no such threat is currently imminent. But Shoemaker-Levy 9 proved that this class of sequential catastrophe is a physical reality. Seeing the solar system's largest planet take these hits shifted our understanding of our own fragility in space. So for 6 days in 1994, we got a live demonstration of what a fragmented comet impact actually looks like, and a sobering hint of what a different orbital angle could have sent toward us instead. Every episode in this arc, all the way back to Chicxulub, has been about an angle nobody chose. Tomorrow, for the first time in 10 episodes, that changes. In 2022, NASA deliberately altered an asteroid's trajectory on purpose, and in 2029, we'll get to test what we've learned when the asteroid Apophis makes its closest approach to Earth in recorded history. Tomorrow, the line we're now drawing.